Hello and good evening everyone. I welcome you all to India's largest e-learning platform, Unacademy. And I welcome you all to Gate Conqueror channel. I welcome you all to my session of Antenna's Maha Marathon series. And today we are discussing about Antenna's Maha Marathon 17. How are you all, dear? This is going to be a very important session, my dear friends. Morning 6 a.m. we are done one session. And we are going to take one more session now, which is a continuation of that. As you know, this is a very special series where almost all the concepts of antennas are covered under single topic. That's why this is a very important concept here, very important topic, where most of the concepts are covered under one roof. Just give me 1 second here. 1 second. One second. Okay. Fine. Good evening, Ravindra. Is the video and audio clear? Please let me know once. Is the video audio clear here? Just let me know once. So this session is about Antenna's Maha Marathon, session number 17. Yes, clear. Thank you, Raj. Thank you. Okay, fine. So before we move in, let me introduce myself. I am GC Reddy. Worked as motivation speaker, Pan India, for the past 12 years. Having overall of 15 years of experience in teaching GATE and engineering aspirants. An expert in the field triangle and the communication square. The field subjects as well as in communication. And this is an official channel, Gate Conqueror, official Telegram channel. You can just make a note of this. You can join us on this particular channel through this particular link where you can access all the Gate Conqueror faculty, including the legendary K.N. Rao sir. And the good news for all the Gate Conqueror followers is we are increased in number now. We got sufficient number of very good faculties so that we can comprehensively complete all the subjects for GATE 2023. Yadav, good evening. That's fine. We are into the subject of antennas. This is Antenna's Maha Marathon series. In this concept of antennas, we completed very important concepts. We'll try to list out them. Antennas concept, completed. Basic terminology of antenna. Current distribution in an antenna. We had seen the radiation mechanism of antenna. And the radiation mechanism of antenna, we covered single wire, two wire, and radiation by a dipole. We had seen the radiation pattern of antenna. In radiation pattern of antenna, we had seen terms like main lobe, side lobes, nulls, first nulls, and back lobe. It seems some special concepts like side lobe ratio or side lobe level. Then we had seen the radiation parameters of antenna. Near about 32 hours of recording is already done, exclusively on antennas and wave propagation here. I can say that you cannot find such detailed explanation about antennas anywhere in this YouTube platform. In radiation parameters, we had seen the important parameters like gain, directivity, efficiency, beam area, and radiation intensity. These are important terms under radiation parameters. Then we had seen the radiation by monopole antenna and dipole antenna. Both are resonant antennas. Let's see the derivation for the same. Discussed about loop antennas. Then we had seen antenna arrays, group of radiators put together geometrically and electrically such that the effective radiation increases. We had seen antenna arrays. In antenna arrays, we had seen two element array, n element array. It's seen the special cases of broadside array, end fire array, we have seen end fire array with increased directivity, also called as Hansen and Woodyard array. Then we had seen special arrays like binomial arrays, as designed by John Stone. This was about antenna arrays. Then we went for the 7 sister antennas. Can you tell me what are 7 sister antennas we discussed? Yes, Srikanth, good evening. What are the 7 sister antennas we discussed here? Yes, anyone? The 7 sister antennas we have discussed. We discussed the 7 sisters. Started with the very important folded dipole antenna, followed by the Yagi-Uda antenna. It is also called super gain antenna or super directive antenna. Then the most famous helical antenna, which is used for generating circular polarization. Yagi-Uda antenna, super gain antenna used for TV reception, TV signal reception. Folded dipole antenna used as a part of Yagi-Uda antenna. Just I am trying to give the highlights of these antennas. You can go through these antennas in detail in the Antennas Maha Marathon series. Already 32 hours of recording is done on antennas. Then we have seen the microstrip array antenna. Then the horn antenna. This is used as feeder antenna or a primary antenna for both parabolic reflector and lens antennas. Then we have seen antennas for long distance communication, which are parabolic reflector antenna, and the lens antenna. These are the 7 sister antennas we have discussed. Besides which, we are also discussed about resonant and non-resonant antennas. Under resonant antennas, we have discussed monopole antenna and dipole antenna. Those are joining new to our session. Just I am trying to give the outline of these wonderful antennas Maha Marathon series. In non-resonant antennas, we discussed about V antennas, inverted V antennas, and rhombic antennas. Other than this, we went for antenna measurements, in which we have discussed the main concept was radiation pattern measurement. Under radiation pattern measurement, we have discussed about gain measurement and directivity measurement. Before that, we had seen the basic setup required for radiation pattern measurement. Then we had discussed about the methods of radiation pattern measurement. High frequency method, where primary antenna and secondary antenna are kept at constant position and secondary antenna is rotated on its own axis. There is a low frequency method. Primary antenna is kept constant and secondary antenna is rotated in a constant radius. Then we had seen the measurement of gain. In measurement of gain, we had seen the first method, a 3 antenna method. Then we had seen the second method, measurement of absolute gain. By 2 identical antennas, by using 2 identical antennas. Then we had seen the measurement of directivity. Directivity is given by maximum radiation intensity to average radiation intensity. It's given by phi max by WAV. It's given as radiated power by 4 pi. This is 4 pi times of phi max by WR, which is double integral of phi of d omega. But d omega is elementary solid angle. So this is a double integral here. Therefore, we need to use graphical numerical methods in order to solve or in order to find the directivity. The graphical numerical methods that we are used are conical cut method, and orange slice method. In detailed explanation about these are already given in our particular sessions. Clear? This was about antennas. Then the second half we started wave propagation. In wave propagation, we discussed about the principal modes of propagation or standard mode of propagation, in which we have discussed about ground wave propagation, are also called as surface wave propagation, are also called as Norton surface wave propagation. Norton's surface wave propagation. It allows frequencies up to 2 MHz. That means it allows very low frequencies, and medium frequencies. Medium frequencies means 300 kHz to 3 MHz. almost most of the medium frequencies it is allowing. Low frequency refers to 30 kHz to 300 kHz. Very low frequency refers to 3 kHz to 30 kHz. Is it clear? So, it allows medium waves. Medium frequency refers to medium waves. Low frequency refers to long waves. And very low frequency refers to very long waves. And in ground wave propagation, the propagation happens through the surface of the ground, through the surface of the earth, along the surface of the earth. And antennas that are employed here are mostly vertical antennas. Any horizontal component of electric field is absorbed by the earth, and this absorption of the earth due to tilting increases with the increase of frequency. Therefore, it is not suitable beyond 2 MHz. And the range of ground wave propagation given by 100 by cube root of frequency given in kilometers, where frequency is given in meters. Where the range is given in kilometers, frequency given in megahertz. That's the formula for range. Range is given in kilometers and frequency given in megahertz. Next is skywave propagation. Skywave propagation, it uses ionosphere. It is also called as ionospheric propagation. Ionosphere contains main layers like D layer, E layer, F1 layer and F2 layer. F1 and F2 layer, they combine at night to become F layer. And ionosphere is a region which extends between 50 kilometers to 400 kilometers above the Earth's surface. And it acts as a mirror to reflect electromagnetic waves. The major contributions was done by A.E. Kennelly and Oliver Heaviside and Sir Appleton. The skywave propagation at its uses, the ionosphere is also called as ionospheric propagation, which reflects between 2 MHz and 30 MHz. Most of the high frequency waves are also called short waves. Therefore, this kind of propagation is also called as short wave propagation. Basically, the capability of skywave propagation depends on the capability of the ionosphere to reflect EM waves. Clear? So that's about skywave propagation. As it allows most of the short waves, it is also called as short wave propagation. Next is space wave propagation. Allows frequency between 330 MHz and 300 MHz, mostly very high frequency waves. For the space wave propagation to be possible, the transmitting antenna and receiving antenna must see each other. They must be at line of sight. For this kind of propagation is also called as line of sight propagation. This space wave propagation mainly contains the direct wave and the indirect wave, and the resultant wave is the sum of direct wave and indirect wave. The major applications of this space wave propagation a TV and FM radio. Ground wave propagation major applications. An AM radio. FM radio will be between 88 MHz and 108 MHz. AM radio will be between 550 kHz to 1650 kHz. And skywave propagation is used for very long distance communication. Using multi-hop communication, round the globe communication is possible using skywave propagation or ionospheric propagation. So this we have discussed. This range is very long or round the globe communication. For space wave propagation, the range is given by, in the morning class we have discussed this. We have derived the expression also. 3.57 into under root of HD plus under root of HR kilometers. Approximated to 4 times of under root HD plus under root HR kilometers. Range is in kilometers and HD and HR in height of transmitter and height of receiver in meters. Okay, clear? Any doubt you can ask, dear? One second. Any doubt so far you can ask? Next is scatter propagation. In scatter propagation we had seen tropospheric scatter, and ionospheric scatter. Tropospheric scatter is mainly because of the blobs formed in the tropospheric region. Blobs are eddies or masses formed in the tropospheric region. When the frequency of operation is less than this eddies or masses or blobs, the wave is scattered in all the directions. Some of the waves will penetrate without any scattering, which are called as no scatter waves. The others will come back to the transmitter side, which is called back scatter waves. Some will move in the reverse direction of receiver, which are called loss scatter waves. But when the frequency of operation is greater than the frequency of the eddies, then the waves will move into the forward cone of alpha, which are called as forward scatter waves, and therefore the tropospheric scatter propagation is also called as forward scatter propagation, using which we can transmit signals range of 160 kilometers to 1600 kilometers. 160 kilometers to 1600 kilometers, frequency range of 100 megahertz to 10 gigahertz. So mostly employs VHF, UHF and a part of SHF frequencies. SHF stands for super high frequencies. Clear? Next is ionospheric scatter, which is mainly because of the sporadic E layer. Can transmit the signal between 1000 kilometers to 2000 kilometers. Frequency range 25 megahertz to 60 megahertz. Only this happens under special conditions, therefore they are not reliable. Similarly, duct propagation happens under special conditions where inversion layers are formed. It undergoes super refraction. Mainly occurs due to the formation of inversion layers, and using the duct acts as a leaky waveguide. It acts like a waveguide and we can pass signals to a distance of 1000 kilometers using this operating frequency 300 megahertz to 30 gigahertz. Is that clear? Next is we are seeing structure of atmosphere. We are discussed about structure of troposphere, structure of ionosphere. A major concept, and we had got lot of emphasis, spent a lot of emphasis on structure of ionosphere especially. And also we derived the derivation for refractive index of ionosphere. The refractive index of ionosphere mu or n is given by sin I by sin r is equal to under root of 1 minus 81 n by f square. We are seeing the mechanism of radio waves bending by ionosphere. At the point where radio waves bend, angle of refraction must be 90 degrees. At this point, mu is equal to sin I under root of 1 minus the place where it bends, n is maximum because refractive index decreases as you move up in the ionosphere. 81 nm by f square. So whenever f square is greater than 81 nm, the waves will bend by the ionosphere because mu will become real. Mu must be real. It can be 0 also. But it should not be imaginary. When f square is less than 81 nm, this value will become an imaginary value. The wave will not bend. So the condition for the wave to bend is f square must be greater than 81 nm. Please make a note of this. Then we are seeing the critical frequency. Critical frequency is the highest frequency that can be reflected back by the ionosphere at vertical incidence. Vertical incidence means incident angle is 0. If you substitute here, I is 0 and R is 90, under root of 1 minus 81 n by f square, this will become sin 0 by sin 90. 0 by 1, 0 implies 0 is equal to 1 minus 81 and its density is maximum 81 nm by f square. In solving this, f is fc. Solving this, you get fc is equal to 9 root nm. This is the formula where fc is critical frequency in megahertz, nm is ionic density in per meter cube. Then we are seeing the concept of virtual height. The virtual height is something which is always greater than the actual height, given by h prime is equal to c into t by 2. Please refer the videos dear. I am just giving you overview now. Please refer the videos for more and more clarity. Some 32 hours of video has been recorded or took live only for antennas Maha marathon. What I am trying to give you is the overview to where we had completed. Almost the theory concept is done. Only 1 or 2 topics are left out in theory that will complete today. Then we will do a lot of practice also. Then we had seen maximum usable frequency, which is always greater than or equal to critical frequency. FMEF and FC are related by FMEF is equal to FC secant I. Secant value is always greater than 1. Therefore, you can say FMEF is always greater than FC. And this is called as secant law. And for F layer, incident angle, the maximum incident angle is possible is 74 degrees. For F layer, secant 74 is 3.6 FC, the standard for F layer. And, we had solved it for Earth is flat. Then you got FMEF is equal to FC into under root of 1 plus d by 2h whole square. The relation between FMEF and FC. Clear? Then least usable frequency is the least frequency that can be operated. It depends on many other factors also. So we need to identify what is the least frequency that is allowed. You can also go through the videos for detailed explanation of this. And from this you got the skip distance. D skip is 2h into under root of FMVO by FC whole square minus 1. This derivation also we have done. And optimum working frequency is chosen as 85% of maximum usable frequency. This is the frequency where we actually work. We try to keep a tolerance of 15%. Clear? Then we had gone through ionospheric abnormalities, in which we had seen sudden ionospheric disturbances are also called as Mongol-Dillinger effect. This is mainly because of gigantic emission of hydrogen from sun followed by solar flares. Gigantic emission of hydrogen followed by solar flares forms Sunspot Cycle. Gigantic emission of hydrogen followed by the solar flare forms the sunspot or a solar flare on the disk, which will be responsible for increasing the least usable frequency greater than the maximum usable frequency, resulting in complete blackout. Ionospheric storms, disturbances in the ionosphere, which will also, because of this, these are also because of the geomagnetic disturbances, which will cause the change in critical frequency. Sunspot cycle is a phenomena which repeats every 11 years, which affects the critical frequency of each layer. Time-side winds, of course, do not have much effect, but they also have a little effect on the communication using ionosphere. Fading is a decrease of signal strength, which is 5 types. It can be selective fading, fading that occurs at selected frequency. Interference fading that is occurring because of the fluctuations of the height of the layers. Absorption fading due to the absorption of the waves. Polarization fading or decrease in signal strength due to change in polarization. And skip fading, this fading that is occurring when you are into the skip distance. Whistlers are naturally occurring electromagnetic transients, which will result in the whistle sounds when the electromagnetic waves pass through the Earth's magnetic field. Next is the Luxembourg effect. Luxembourg effect is mainly, it got this name because of the station Luxembourg. A high frequency station called Luxembourg was able to hear a low frequency station called Paris as background. This occurs when a low frequency station is between the transmitter and the actual high frequency station. So high frequency station can hear the low frequency station as background. This is called ionospheric cross modulation. This was first observed by the Luxembourg users, which is operating at 230 kHz. We are able to hear the Paris station signal, which is operating at 182 kHz. As it was first observed by the Luxembourg users, it is also called as Luxembourg Effect. Next are statics or atmospheric noise, or atmospherics are naturally caused noise. Man-made noise, as indicates, it includes all the different kinds of possibilities of man-made noise. Polar cap absorption, a decrease in the signal strength due to formation of solar proton event, mainly occurs in the polar region. Ionospheric absorption can be divided into two types: non-derivative absorption and derivative absorption. Non-derivative absorption is very close to the Earth, where mu is approximately equal to 1, or refractive index is approximately equal to 1. Derivative absorption at larger heights, where mu is far less than 1. And in the morning session also, we had seen range of space wave propagation. It has 3.57 times of under root HD plus under root HR kilometers. This can be approximated to 4 times of under root HD plus under root HR kilometers. Then we had seen the effect of Earth's curvature on space waves, and we came to know that even if you take the flat Earth surface or the curved Earth surface, the received electric field strength is same. For detailed explanation, you can go through AMM 60 India, where I had explained very detailedly how received electric field strength will not change based on the curvature. Then we have derived the expression for received electric field strength, what as 88 root P HD HR by lambda D square volt per meter. This is the received electric field strength for space waves. This almost completes all the derivations. What we are left out with fading, a small part that is left out is fading and path loss calculation, which will complete the complete wave propagation concept. With this, the theory of antennas and wave propagation will be done. Then we will do lot of practice problems, followed by solving previous year question papers of GATE and engineering services. And I promise to give you some more practice problems, around 100 to 150 practice problems in antennas Maha Marathon 19 and 20. But right now we are into 17. Any doubts so far? Please let me know, dear. Any doubts, please let me know. Is the video audio clear? Next is fading. Fading is defined as the variation of refractive index. Fading can be fast fading, slow fading, single path fading, multi path fading, short-term fading and long-term fading. Fast fading generally occurs very fast. It will be in milliseconds or microseconds. Slow fading, it fades. Decaying process happens very slowly. Single path fading, fading of a signal which is directly transmitted to receiver, and a multi-path fading occurring due to the interference between the signals. Short-term fading which sustains for only small time. Long-term fading, the decreased signal strength will be in that state for more time. Fast fading and multi-path fading, the fading will be for lesser duration, like 0.01 second. Again the signal will get back to its original strength. Long fading, you can see fading of 10 dB is also possible in the case of long fading. As you know, for every 3 dB the power will become half. 6 dB the power will become 1 by 4. 9 dB the power will become 1 by 8. I told you shortcut previously. Minus 10 dB means the power will become 1 by 10. The signal strength is decreasing to 1 by 10th, which is very huge amount of loss, 90% loss. That's why long fading may also result in fading resulting in loss of 10 dB. In order to overcome the fading, we use diversity techniques in the receiver. The diversity techniques include space diversity, frequency diversity, time diversity, modulation diversity, and polarization diversity. In summer, the signals are 10 dB stronger than the other seasons. In summer, morning and evening, they are 5 dB stronger. Got it? Everyone, is it clear? Please let me know, dear. Everyone, please let me know. Is that clear? Everyone. Any doubts, please let me know. Any doubts, dear? Next is path loss calculation. Path loss calculation. Path loss calculation is given by 32.45 20 log to base 10 of frequency in megahertz, 20 log to base 10 distance in kilometers. This standard formula for path loss calculation. And path loss in decibel. And And path loss in decibel is given by total path loss in decibel is free space loss plus scattering loss plus reflection loss plus fading loss, coupling loss plus gain of transmitter minus gain of receiver. This is measured in decibel. This is measured in decibel, in which free space loss is given by 10 log to base 10. This is in decibel. So 10 log to base 10, 4 pi d by r whole square. R is the distance. And scattering loss is given by 57 plus 10 times of theta minus 1, where theta is calculated as theta naught minus theta 1 minus theta 2, where theta naught is the intersection angle. Where theta naught is the intersection angle. Any doubts you can ask, dear? Where theta naught is the intersection angle. 10 log of frequency in megahertz by 400, where theta naught for all values of theta naught greater than 1, where theta naught is the intersection angle, from which you can find theta. Reflection loss is defined in terms of capital Ns. Capital Ns is defined in terms of small ns, where small ns is surface refractive index, and coupling loss is something related to the gain of transmitter and gain of receiver. The formula is given there. Is it clear, everyone? Path loss calculation formulas are very, very important. Path loss calculation formulas are very, very important here. Please take a screenshot of this. Path loss calculations. Everyone. Everyone. Sorry. It's about path loss calculation. So everyone do this, dear. Calculate path loss for a communication system operating at 100 megahertz and 100 kilometers. Path loss, calculate path loss for a communication system operating at 100 megahertz and 100 kilometers. What is path loss formula? 32.45 plus 20 log frequency megahertz to base 10, 20 log distance in kilometers to base 10. Please substitute and find the answer. Yes, everyone try to substitute and find the answer, dear. Calculate everyone fast. Fast, dear. What is the answer? $32.45. What answer you got? 20 log to base 10, frequency in megahertz, 20 log to base 10. Distance in kilometers. 32.45. 110 square. Log m power n. N log m. So 40 log 10 to base 10. 40 log 10 to base 10. 80 plus 32. 112.45. You got the same answer? Option C is the answer. Everyone try to calculate this. Calculate total loss in decibel for a communication system having free space loss of 20 dB, scattering loss of 10 dB, reflection loss of 5 dB, fading loss and coupling loss of 3 dB, gain of transmitter 100, transmitting antenna 100, and gain of receiving antenna 10. This is for total loss in decibel. Please calculate. Please calculate. Calculate and let me know the answer. I am also calculating. Everyone please calculate. Calculate and let me know, dear. Just as fast. Free space loss 20 dB, scattering loss of 10 dB, reflection loss 5 dB, fading loss 3 dB, coupling loss 3 dB, gain of transmitting antenna 100, convert into decibel, 10 log GT to base 10. Ten log 100 to base 10 is 20 dB. Minus gain of receiving antenna again is 10 in decibel. 10 log 10 to base 10. It's 10 dB. Minus 10 dB. Calculate. $30, $35, $38, $41, $61, minus 10, 51 dB. Option B is the answer. You got the same answer here, everyone? Do the calculation and let me know. Do you got the same answer? Yes, everyone. Just let me know. Do you got the same answer? Free space loss 20 dB. Scattering loss 10 dB, free space 20, scattering 10, reflection 5, fading coupling 3, transmitting antenna gain 100, in terms of decibel it is 20 dB, receiving antenna gain 10, in terms of decibel it is 10, yes 51 dB. Please verify and let me know everyone. Everyone. Yes. Next question. Expression for critical frequency is given by. Expression for critical frequency. What's the answer? Expression for critical frequency. Refractive index N or mu is equal to sin I by sin R under root of 81 Nm by F square. Critical frequency, incident angle is 0 or vertical incidence, angle of refraction 90 degrees, N is Nm and F is equal to Fc, implying N is sin 0 by sin 90 under root of 1 minus, initially you can give it as N. At that point N is Nm, the point where it bends. One minus 81 Nm by Fc square. Sin 0 is under root of 1 minus 81 Nm by Fc square. Implies 0 is 1 minus 81 Nm by Fc square. Implies 1 is 81 Nm by Fc square. Implies Fc square is 81 Nm. Implies Fc is 9 root Nm. Where Fc is critical frequency in megahertz, Nm is ionic density in per meter cube. Any doubts, please let me know. Any doubts, please let me know. Clear? So 9 root Nm. Option C is the answer. In the expression for critical frequency, Fc is equal to 9 root Nm. Nm is ionic density per meter cube. Then Fc is expressed in, just now I told you, if Nm is ionic density in per meter cube, Fc is expressed in megahertz. Option B is the answer. Yes. Any doubts you can ask? Clear? Virtual height is always dash than the actual height. The curvature of the earth. The ionospheric layer starting at 50 kilometers, ending at 400 kilometers. A wave that is sent upward will enter the ionosphere, continuously refract and come back. Receiving antenna. 1 second here. Try to draw it more neatly. Yeah. The curvature of the earth. Okay. The ionosphere. The ionosphere starting at 50 kilometers, ending at 400 kilometers. From 50 to 90 kilometers, (50 to 90 kilometers), it's a D region. (90 to 140), it is E region. 140 to 400, it is the F region. And the wave is entering continuously, it undergoes refraction and it will come back like this. This is the actual height to which it has went up. But if you take the projection, because from here we don't know how much refraction is taking place and where it actually bends back, where angle of refraction is becoming 90, we cannot guess. So what we do is we draw the projections, and this is the intersection point. And this height, the projected height, is called the virtual height H prime. And this height, to actually which it is propagating, is the actual height HA. Virtual height is always greater than the actual height. And how to find this? The wave is propagated with velocity of c. Velocity is distance by, let capital T is the time taken for two-way time taken for the wave to go up and come back. T by 2 is the time taken to go up. If you send an impulse vertically upward, total time taken for the impulse to go up and come back is T. Half of the time is T by 2. Velocity is distance by time. Speed is distance by time. C is h by T by 2 or h prime. The virtual height is C into T by 2. It is also clear that virtual height is always greater than the actual height. So what's the answer here? Option B is the answer. Clear everyone? Option B is the answer. Virtual height is always greater than the actual height. Expression for virtual height. H prime, just now I derived you. Speed is equal to distance travelled by time. Time T by 2 is the time taken for the impulse signal to vertically move upward. And T is the two-way time. H prime is equal to C into T by 2. H prime is equal to C into T by 2. Clear? Next question. Maximum frequency that can be reflected back by the ionosphere at any given angle of incidence is called as. The maximum frequency that can be reflected back by the ionosphere at any angle of incidence, by definition, the maximum frequency that can be reflected back by the ionosphere at any angle of incidence is called as maximum usable frequency and is related to the critical frequency as FMEF is equal to FC into secant I, which is called as Secant Law. Clear? So what's the answer? Option C is the answer. FMEF and FC are related to each other by the expression from Secant Law. FMEF and FC are related by FMEF is equal to FC into secant I. From Secant Law, FMEF is equal to FC into secant I. Option B is the answer. Any doubts here? For F layer, the value of I is dash degrees. For F layer, I told you, the value of I is the possible incident angle. The maximum possible incident angle for F layer is dash degrees, 74 degrees. Option B is the answer. When I is dash degrees, FMEF is equal to FC. You know that from Secant Law, FMEF is equal to FC into secant I. For what value of I, both FMEF and FC are equal. The incident angle is 0. Secant 0 is 1. Both FMEF and FC are equal, and by definition also, maximum usable frequency is the maximum frequency that can be reflected back by the ionosphere at any incident, whereas critical frequency is the maximum frequency that can be reflected back by the ionosphere at vertical incidence. Vertical incidence means incident angle is 0. Therefore, option A is the answer. Any doubt? You should be very carefully at here. Bhaskar, good evening. Any doubt, Bhaskar? Any doubt? A dash incidence FMEF is equal to FC. A dash incidence FMEF is equal to FC. What is the answer here? We know FMEF is equal to FC secant I from Secant Law. We also know that FMEF is always greater than FC. We also know that when incident angle is 0, FMEF is equal to FC. And by definition, critical frequency is the maximum frequency that can be reflected back by the ionosphere yet vertical incidence or incident angle is 0. So, When incident angle is 0 means what? What it is called? Bhaskar, what it is called? It is called as vertical incidence. A dash incidence FMEF is equal to FC at vertical incidence. Vertical incidence refers to incident angle is 0. When incident angle is 0, you know that FMEF is equal to FC. So, question number 9, option A is the answer. Clear? For flat earth, FMEF and FC are related by. For flat earth, FMEF and FC are related by. You know, FMEF is equal to FC into secant I. If you consider a flat earth and you consider a thin ionospheric gradient, the transmitter, there is the receiver, total distance is D, this is D by 2, this is D by 2, this is H over here, the thin gradient, this is the incident angle, and this is the refraction angle. From this is the right angle triangle over here. This is the transmitter point, the receiver point, this is the center point. Some be point B. You know, FMEF is equal to FC into secant I. From this, cos I is equal to, this is 90 degrees, so this is hypotenuse. This is opposite and this is adjacent. Cos I adjacent by hypotenuse. H by hypotenuse under root of side square plus side square. H square plus D by 2 whole square. This is cos I. If you take secant I, under root of H square plus D by 2 whole square by H. From this secant I is, take H square common and take it out of the root, it will become H. H and H get cancelled. Under root of 1 plus D by 2H whole square. Therefore, FMEF is equal to FC into secant I under root of 1 plus D by 2H whole square. This is the formula. Any doubt here? And this is the derivation for it. Therefore, FMEF is equal to FC into under root of 1 plus D by 2H whole square. Question number 10. Option C is the answer. Please let me know. Any doubt? Everyone, any doubt? For a curved earth, FMEF and FC are related by. Yes, tell me dear. You know FMEF is equal to FC into secant I from secant law. For flat earth, FMEF is equal to FC into under root of 1 plus D by 2H whole square. Just now I derived the derivation for the same. For curved earth, FMEF is given by FC into under root of D square by 4 H plus D square by 8R whole square H plus D square by 8R. Is it clear? So 11th question, option D is the answer. Expression for maximum skip distance. Just see here carefully, dear. Okay. See here carefully. What you got here, dear? FMEF is equal to FC into secant I. This is called as secant law. For flat earth, FMEF is equal to FC into under root of 1 plus d by 2h whole square. I want d skip derivation. Please do it and tell me. Everyone, please do the d skip derivation and tell me. First, from this FMEF by FC, under root of 1 plus d by 2h whole square, squaring on both sides, FMEF by FC whole square is equal to 1 plus d by 2h whole square. From this FMEF by FC whole square minus 1 is d by 2h. Whole square. From this d by 2h is under root of FMEF by FC whole square minus 1. From this d skip is 2h into under root of FMEF by FC whole square minus 1. Clear? Any doubt, let me know, dear. You can chat to the chat box, dear. Clear? So for maximum skip distance, this is d skip. The maximum skip distance is given by under root of 8HR. Very important formula, dear. The maximum skip distance under root of 8HR. Question number 12, option B is the answer. As operating frequency decreases, effect of noise as operating frequency decreases, effect of noise, as frequency decreases, noise will increase. The effect of noise increases. Question number 13. We have discussed about this in detail in least usable frequency concept. So question number 13, option B is the answer. The expression for skip distance is, just now we have derived now, Bhaskar, how much it is? D skip is 2h into under root of FMVF by FC whole square minus 1. Option B is the answer. Question number 14, option B is the answer. One second here. One second. Fine. Yes, everyone, just give me one moment, okay? Fine. Okay. Next question number 15. Optimum working frequency is dash percentage of maximum usable frequency. We discussed now. Optimum working frequency is 85% of maximum usable frequency. Question number 15. Option A is the answer. Next. Someone tell me this question, dear. Mongol-Delinger effect. Mongol-Delinger effect is also called as Mongol-Delinger effect. In ionospheric abnormalities, this is the first one. Mongol-Delinger effect. Mongol-Delinger effect is also called as the first of the ionospheric abnormalities. Sudden ionospheric disturbances. Why it occurs? Due to gigantic emission of hydrogen from sun, which are followed by X-rays, forming a bright spot on the solar disk, resulting in least usable frequency increasing more than maximum usable frequency, resulting in a complete blackout, which is called as sudden ionospheric disturbances, first observed by Mongol and Delinger. Therefore, it is also called as Mongol and Delinger effect, or simply Mongol-Delinger effect. Is that clear, everyone? Ionospheric storm have tendency of reoccurring in intervals of dash days 23.7, 27.3, 37.2, 32.7, 27.3 sun's rotation time. 17th question, option B is the answer. Sunspot cycles have an average period of dash years. I discussed this here. Sunspot cycles have an average period of dash years. Sunspot cycles have an average period of 11 years. They repeat every 11 years. Option C is the answer. Okay. Luxembourg Effect. It was observed first by the Luxembourg users. Luxembourg Effect is also called as, that means a high frequency channel will listen a low frequency channel as background. When a low frequency channel is in between the transmitter and the high frequency channel, this effect is called the Luxembourg Effect. Also the technical term for this is called as Ionospheric cross modulation. Ionospheric cross modulation. Question number 19. Luxembourg Effect is also called as Ionospheric cross modulation. Question number 19. Option B is the answer. Statics are, what are statics? Naturally caused noise, man-made noise, both or none. Statics refers to atmospherics. Which are naturally caused noise. Question number 20. Option A is the answer. Okay. Calculate this dear. In space wave propagation, if height of the transmitting antenna is 100 meter and height of the receiving antenna is 100 meter, range of space wave propagation is approximately dash kilometers. Calculate. Everyone calculate here. I am also calculating. You people please calculate. Calculate dear. Calculate and let me know the answer. First, Bhaskar, Karna, everyone. What is the formula? Range is 3.57 under root HD plus under root HR kilometers. Remember, HD is height of transmitter given in meters, HR is height of receiver given in meters, and range is given in kilometers. 3.57 under root 100 plus under root 100 kilometers. 3.57 into 10 plus 10, 20. 71.4 kilometers. That is what you got, range. Everyone verify. Everyone verify. Yes. The magnitude of electric field strength of space waves is given by, we derived this derivation now, mod of ER is equal to 88 root P HD HR by lambda D square volt per meter. 88 root P HD HR by lambda D square. Option B is the answer. Everyone tell me there any doubts so far? Please let me know. Completed the complete theory regarding antennas. We are doing practice questions. We will do more and more practice questions. Tomorrow, 6 a.m. There is one more session where you can do more practice there. So far, any doubts, please let me know here. Any doubts? Good one. Now we'll do some previous year question papers, dear. First one, try to answer the first one. Try to answer the first one. These are all previous year question papers. These are all from previous year question papers. Some of them appeared for engineering services, some of them appeared for GATE. For an aperture antenna, aperture dimension capital D and wavelength lambda. The far field is at a distance greater than. The far field is at a distance greater than. When you consider an antenna, with its largest dimension capital D, around the antenna, very close to it, this radius is R1. After that, the radius is R2. R1 is of radius 0.62 into under root of d cube by lambda. R2 is less than or equal to 2d square by lambda. And then this sphere with radius R1 is called reactive near field region, and the one with R2 is called radiating near field region, also given after the name of scientist called as Fresnel region, above which, where R is greater than 2d square by lambda, this outer space, remember these are all spheres, this outer space where R greater than 2d square by lambda, this outer space refers to far field region, also called as Fraunhofer region. If you want to do any measurement of any radiation parameters, we do it in the far field region or Fraunhofer region. Now you see the question for an aperture antenna with aperture dimension d, wavelength lambda, the far field is at a distance greater than, what is the radius of the far field? R greater than 2d square by lambda. This is called far field region, where you can measure all the radiation parameters of the antenna. Now you may ask me, sir, why we shall do it only in the far field region? Why we must do it in the only in the far field region? But then let me answer that. Why only in the far field region? If you want to know why only in the far field region, just give me 1 second. I'll explain. With an example, I'll explain. Give me 1 second here. See this diagram. See this diagram. Very nearer to the antenna, that is reactive near field region. Disturbance is more. As you move ahead, you got into radiating near field region, but both are near field regions only. And this region is called Fresnel region. After that, it is far field region. Now you can see in the far field region, there is uniform distribution. Radiation parameters can be measured here. That's the reason we must measure all the radiation parameters of antenna only in the far field region. Is that clear? Everyone, is that clear? Next question. In microwave communication links, the raindrop attenuation experience is mainly due to, in microwave communication links, the raindrop attenuation experienced is mainly due to absorption of microwave energy by water vapor, resonance absorption of atomic vibration in water molecules, scattering of microwaves by collection of water drops, refraction of microwaves through liquid drop lenses formed by rain. Think and try to answer the question here. Think and answer. You know, in microwave communication links, Attenuation is mainly due to water drops, collection of water drops. We also call it as rainwater attenuation, very high. Option C is the answer. In line of sight communication system, that means space wave communication system, the ground below the direct path is the first Fresnel zone and is smooth reflecting. The phase difference between direct wave and indirect wave, I told you in theory, in the morning session also, the phase difference between direct and indirect wave is how much, dear? Think and answer. The phase difference between the direct wave and indirect wave is how much? The direct wave and indirect wave, the space wave communication or line of sight communication between transmitting antenna and the receiving antenna, there will be two kinds of waves. One is the direct wave, that is reaching directly from the transmitting antenna to the receiving antenna. Other reaching after reflecting from the earth surface. The one that is reaching directly from the transmitting antenna to the receiving antenna is called the direct wave. The one that is reaching after reflection from the earth surface is called indirect wave. And the difference or the phase difference between direct wave and indirect wave is by default 180 degrees. Question number 3. Option A is the answer here. Clear? Next question. Very important. The antenna has 40 ohm antenna resistance. Antenna resistance are also called as antenna loss resistance. How much given? 40 ohm. And the radiation resistance given as 60 ohm. Is asking us to find the efficiency of the antenna. Find out here percentage efficiency. Find out percentage efficiency, everyone. RR radiation resistance is given as 60 ohm. Loss resistance is given as 40 ohm. Is asking us to find percentage efficiency. Try to find out. Efficiency is given by the ratio of power gain to directive gain. It's given as radiated power by total input power. We know total input power is radiated power plus loss power. Radiated power is I square RR, where RR is radiation resistance. WR is I square RR plus WL is I square RL, where RL is loss resistance. Efficiency is given by RR by RR plus RL formula. Percentage efficiency RR by RR plus RL into 100. RR is given as 60. RR plus RL 60 plus 40 100 into 100. Percentage efficiency 60%. Therefore, option D is the answer. Is it clear? Next, calculate this dear. If the height of transmitting and receiving antennas in a line of sight system 49 meter and 9 meter respectively, the distance up to which the communication is possible means range. Range is given as 4 times of under root HT plus under root HR kilometers, where HT is height of transmitter in meters and HR is height of receiver in meters. 4 times under root 49 plus under root 9 kilometers. 4 times under root 49, 7, under root 9, 3. 10 into 4, 40 kilometers. Option A is the answer. Clear? The skip distance is same for each layer, independent of frequency, independence of state of ionization, independence of transmitted power. Independent of transmitted power. Very, very, very important question. Listen carefully, think carefully and answer here. Very important question. Let me see who will answer it correctly. Very, very important question. Think carefully and answer. It's a logical question. Please think carefully and answer. Everyone think carefully and answer. If you go for skip distance, if you see the relation between FMEF and FC, FMEF is equal to FC into secant I. Earth is flat, FMEF is equal to FC into under root of 1 plus d by 2h whole square. Solving this, already in this class we have done this. We got skip distance, d skip as 2h into under root of FMEF by FC whole square minus 1. The formula for skip distance. Now he's saying skip distance is same for each layer. Each layer, if you take ionosphere will be between 50 kilometers to 400 kilometers above the Earth's surface. 50 to 90 kilometers it is D layer or D region. 90 to 140 it is E region. 140 to 400 it is F region. We know this, am I right? Now, skip distance is same for each layer. Each layer is a different height. H is varying. Skip distance will be different. So this is not the correct option. It is independent of frequency. No choice. You can see here. Skip distance depends on frequencies. It is not independent of frequency. No choice. Independent of ionization. Here it depends on FC. FC is 9 root Nm. Nm is ionization. Depends on FC means it depends on ionization. No. It is independent of transmitted power. Yes. It does not depend on transmitted power. Very, very important question. Question number 6. Option D is the answer. Option D is the answer. Is it clear? Next, in troposcatter links, diversity system is mainly used to increase the bandwidth, increase the directivity of the antenna, prevent noise effects, detect signal in the presence of fading. Think carefully and write the answer. Think carefully and tell me the answer here. In troposcatter links, diversity system is mainly used to increase the bandwidth, increase the directivity of the antenna, prevent noise effects, detect signal in the presence of fading. Please let me know the answer. I told you when I was discussing theory, there are some pair words you need to remember for easy answering. Wherever fading is there, it's a problem of decrease of signal strength. The solution is diversity reception. Wherever there is fading, the solution is diversity reception. In troposcatter links, diversity system is mainly used in which cases? To detect signal in the presence of fading, that is decrease in signal strength. Fading and diversity system are pair words. Therefore, option D is the answer. Got it, everyone? Clear? Next question. If Skywave with a frequency of 50 megahertz is incident on a D region at an angle of 30 degrees, angle of refraction is dash degrees. Logical question here. It's a very good question. Logical question. Try to think and answer. It's a logical question here. Try to think and answer. Try to think and answer. It's a logical question here. If a Skywave with a frequency of 50 megahertz is incident on D region at an angle of 30 degrees, the angle of refraction is, if you go for the derivation for refractive index, N or mu is given by sin I by sin R under root of 1 minus 81 n by f square. For the wave to bend back by the ionosphere, mu must be 0 or any real value which is less than 1. So, mu must be less than 1, but it can't be imaginary. It must be real. So for ionosphere, we can say that for ionosphere, refractive index mu or n is less than 1. Therefore, sin I by sin R, which is mu, is less than 1. Implies sin I For ionosphere, sin I is less than sin R. I is less than R. I is less than R. Given I is 30 degrees, R must be greater than I. So not 15, not equal to, not 5.5. The only logical answer left out is option B. That's why it's a super question. Question number 8, option B is the answer. Everyone got the logic here? Yes, everyone got the logic? Please let me know. Okay. Next. Question number 9. While determining antenna height for terrestrial microwave links, the effect of refraction from the atmosphere is taken care by considering effective curvature of the earth to be. Effective curvature of the earth to be. How much is considered? In theory, I told you. In determining the antenna height for terrestrial microwave links, the effect of refraction from the atmosphere is taken care by considering the effective curvature of the earth to be 4 by 3 times of the radius of earth. Very important question here. We discussed this in theory. Option C is the answer. Question number 9, option C is the answer. Next question. For producing circularly polarized beams in microwave communication field, the type of antenna ideally suited is, again, it depends on pair words. I told you. What is given? We need circular polarization. Tell me dear, which is the antenna that is best suited for circular polarization? Tell me. Tell me everyone, what is the antenna that is best suited for circular polarization? Think and tell. Think and tell. Wherever there is circular polarization, the pair word is helical antenna. Helical antenna is the best antenna that is suitable for circular polarization. Just like fading is a problem, diversity reception is a solution. Just like fading and diversity reception are pair words, helical antenna and circular polarization are pair words. So, for producing circularly polarized beams in microwave communication field, The antenna that is ideally suitable is helical antenna. Question number 10, option A is the answer. In cellular communication systems, path loss between transmitter and receiver is due to. Now, this is also very good, interesting question. Try to think and answer. This is also very good question, dear. Try to think and answer. In cellular communication system, path loss between transmitter and receiver is due to. Cellular communication system uses line of sight. That's the basic information you should know first. That cellular communication uses line of sight. Line of sight means the transmitting antenna and the receiving antenna will see each other, and we have direct wave and indirect waves. In cellular communication system, path loss between transmitter and receiver is due to scattering from buildings. Between transmitter and receiver, you may have some buildings that are placed there. There may be some trees. There may be some vehicles. And other structures. Something like mountains and all. In cellular communication system, where we use line of sight, path loss between transmitter and receiver is due to scattering from buildings. Yes. The signal, this is a direct wave, this is an indirect wave, is interacting with all this and getting scattered, and the signal strength is decreasing, resulting in path loss. So the path loss is because of scattering from buildings, yes, from trees, vehicles and other structures only. If these are not present, the signal is in this way. If they are not present, but now that if they are present here, when they are interacting, the signal strength is decreasing. It's a very low signal you are able to receive. So this is true, no doubt. Second reason at A, that is this one above, and due to reflection from ground only. Not only that, the signal strength is decreasing because of scattering with buildings, trees, vehicles and other structures, but also because of the reflection from the earth surface. Yes, this is true completely. This is also true. That means this point is already included in this. B can be the answer. Let us see. Next, reasons at A and B, all this, and also reflection from ionosphere. Now you tell me, cellular communication system uses line of sight, which happens in troposphere. Does it have anything to do with ionospheric reflections, where ionosphere is between 50 to 400 kilometers? Is this having anything to do with that? Nothing, I'm right. That's why this is not the answer. And this is very clear. A, B, C is there. C is already not the answer. So need not read, but still if you read, along with surface loss due to surface wave or ground wave propagation. We are not talking about ground wave propagation. Basically, you need to understand is cellular communication uses line of sight. If you understand this, cleverly you can remove this too. Therefore, all A is included here. Reflection is also included. Beautiful question. Question number 11. Option B is the answer. Question number 11. Option B is the answer. Got it, everyone? Consider the following statements. For space communications, the carrier frequencies are generally greater than 108 megahertz. Why they are greater? He is trying to give a reason. Because it is desirable to avoid interference due to FM band. Now, what is FM band here? FM band is in between 88 megahertz to 108 megahertz. And in space communications, the carrier frequencies are generally greater than 108 to avoid interference from FM band. Yes, FM band is up to 108. If you maintain more than 108, it will avoid interference with the FM band. One is absolutely true. One is not present in C, so this is not the answer. It can be A, B, D. Now, next, to penetrate the ionosphere without any reflection. Ionosphere can reflect frequencies between 2 megahertz to 30 megahertz only. Above that, it will penetrate. Yes, true. To increase the coverage area, higher frequencies, if they are operated, we can cover higher areas or larger areas. Yes, true. Third one, to have less skip distance. To have less skip distance. Skip distance 2h into under root of FMU by FC whole square minus 1. Skip distance here is something that is related to the incident angle. Is something that is related to the incident angle. The higher it goes, the deeper it goes into that ionosphere. It will come back from the ionosphere very close. Thereby the skip distance decreases there. What is saying here? Frequencies more than 108 megahertz are used to have less skip distance. If 108 megahertz, more than 108 is used, the wave will not reflect at all. Skip distance concept will be there only when we are using ionosphere. Ionosphere can only reflect between 2 megahertz and 30 megahertz. At 108 or above 108, there is no concept of skip distance only. Increase of skip distance or decrease of skip distance, because skip distance concept we should talk only when we are talking about ionospheric propagation. Above 108 megahertz, ionospheric propagation is not possible. Therefore, you need not talk about skip distance. 1, 2, 3. Option A is the answer. 1, 2, 3. Option A is the answer. Clear? Therefore, option A is the answer. Question number 12. Option A is the answer. Any doubt here? Yes, please let me know. Any doubt, please let me know, dear. Clear? Thirteenth question. Consider the following types of modulation: amplitude modulation, frequency modulation, pulse modulation, and phase modulation. Which of the above modulations are used for telecasting TV programs? In a television system, we have mainly two signals. One is video signal, other is audio signal. For video signal, we use an envelope using amplitude modulation. Using amplitude modulation. Audio, we use frequency modulation. So for video, we employ AM. In AM also again we will have positive modulation and negative modulation. We use negative modulation. Negative modulation means increase of amplitude with the decrease of signal strength. Vice versa concept. So for video we use amplitude modulation, for audio we use frequency modulation. We use amplitude modulation for video, and for audio we use frequency modulation. 1 and 2. Option C is the answer. Question number 13. Option C is the answer. Hello Deva. How are you? This is Antennas Maha Marathon series, Deva. Everything about antennas is here. This is session number 17. Almost 35 hours of recording we have done. Any doubt on antennas, you can just refer this particular series. Your doubts will get cleared. All your doubts will get cleared. Generally antennas, they take 6 to 7 hours max on any YouTube platform. We are already into the 35th hour for this AMM series. Complete antennas will be there here for you. Is it clear, Deva? Any doubts? We had finished the complete theory. And we are now doing the practice problems or the previous year question paper problem. Then we will do the practice problems also. Tomorrow 6 a.m. we have Antennas Maha Marathon 18, where we will do some more practice questions along with the previous year questions. Yeah. Anyone, any doubt, please let me know, dear. Any doubt, please let me know. Next question. In microwaves, communication system using circularly polarized beams. The receiving antenna should be, already I told you, pair word. The pair words are wherever there is helical antenna, pair word is circular polarization. For circular polarization, the best antenna is helical antenna. These are pair words. You are using circularly polarized beam, circular polarization. So the antenna must be helical antenna. Antenna must be helical antenna. So question number 14. Option A is the answer. Clear, everyone? Next question. The extended range propagation. See the word carefully. Extended range propagation occurs due to high conductivity of the ground, low conductivity of the ground, blobs or masses or eddies of different dielectric constants randomly distributed in the volume of the upper atmosphere. High conductivity of upper atmosphere. Almost A, B, D are telling only about conductivity of the ground and conductivity of the upper atmosphere. But when I see here extended range of propagation, that means what? Communication happening beyond horizon, beyond line of sight. Beyond line of sight communication means scatter communication or scatter propagation. This scatter communication or scatter propagation is of two types. Tropospheric scatter and ionospheric scatter. Tropospheric scatter. It happens in frequencies in the range of 100 MHz to 10 GHz, where you can send the signal or the wave in the range of 160 kilometers to 1600 kilometers. And tropospheric scatter, in tropospheric scatter we employ high power VHF or UHF antennas, both facing towards the common volume in the troposphere. As you know, troposphere is also called the region of change. Atmospheric conditions change very quickly, frequently forms a turbulence region. Turbulence region is nothing but blobs of masses or eddies, different dielectric constant move in random directions to form a disturbance region called turbulence region. And the wave from the transmitting antenna, when it is transmitted facing the common volume of this turbulence region, when the frequency of the wave is less than the frequency of the eddy, then the wave, some of the waves will go in the same direction without any scatter. These are called as no scatter waves. Some of them will return back. These are called back scatter waves. Some of them will move into the forward region, that is for different condition where frequency is greater than Fe or the frequency of the eddies. they move into the forward region. But when they are less than that, some of the waves will also move in the backward direction, exactly opposite of where receiver is placed. These are called lost scatter. But when frequency is greater than the frequency of eddy, they will move into the forward angle of alpha. As the communication is happening because of forward scatter waves, these are called forward scatter waves. Therefore, the tropospheric scatter is also called as forward scatter propagation. And because of this, communication is happening beyond line of sight. Now, if you read the question, extended range of propagation beyond line of sight occurs due to blobs of different dielectric constant or masses or eddies randomly distributed in the volume of the upper atmosphere. Absolutely. What he's talking about? He's talking about tropospheric scatter. Therefore, option C is the answer. Question number 15, option C is the answer. Any doubts? Any doubt here? Sixteenth question. In line of sight propagation systems, to take account of normal refraction and effective earth radius factor K is used, whose value is effective earth radius factor. Effective earth radius factor is something that will tell you about the factor by which the radius of earth is greater, considered in line of sight propagation calculations. As you know, it is a customary thing that we take 4 by 3 times of the radius of earth. This 4 by 3 is called effective earth radius factor given by K. K times the radius of earth. K is given by 4 by 3. Question number 15. Option A is the answer. Most of you people know this, but you should know K is called as effective earth radius factor. Most of the people know that we take 4 by 3 of the radius of the earth, but they don't know that this 4 by 3 is called as effective earth radius factor. It is important to note down that it is called as effective earth radius factor. Clear? Microwave link repeaters are typically 50 kilometers apart because of atmospheric attenuation, because of output tube power limitations, because of curvature of earth, to ensure that the applied DC voltage is not excessive. Why microwave link repeaters are placed 50 kilometers apart? Why they are placed 50 kilometers apart? Because you know the range of line of sight communication is 3.57 under root HT plus under root HR kilometers. Maximum height that you can keep it for the transmitting antenna and the receiving antenna. This is also not practical dear, but okay, we can take. Is 100 meter and 100 meter. In that case, the range will become 3.57 times under root 110 kilometers. 20 into 3.57, 71.4 kilometers. This is maximum theoretical value. Practically, you cannot go up to 71.4, So it's a customary thing that microwave link repeaters are placed after every 50 kilometers because we lose line of sight, and we lose line of sight because of earth curvature. We lose line of sight because of earth curvature. Therefore, option C is the answer. Question number 17. Option C is the answer. Clear? Have you covered these topics in this series? Modulation and demodulation systems, types of transmission lines, losses, standing waves, ground and space wave propagation. Yes, Deva, we had covered ground wave, skywave and space wave propagations. The other topics that you are speaking about will cover in transmission lines. After antenna series, tomorrow at 9 p.m. I am starting and I am continuing, I'm continuing wave propagation. But day after tomorrow we'll complete that. Then we'll follow up with transmission line series. In transmission line series, I'll try to cover it up. This is antenna series only. Only about antennas. What we had discussed in this antennas, I had already explained at the start of this class. Please go through it. There are 17 videos, including today's. There are 17 videos. 35 hours of recording is available only on antennas. The rest of the topics that you are talking about, that is related to transmission lines, will be covered in EMFT Module 3 transmission lines. Is it clear, Deva? Let me know, dear. If you go through the series, if you go through the playlist, things will be very, very clear, Deva. Okay? You are into which year, Deva? Are you still into are you final year? Third year or a final year student, or you are passed out? Are you a passed out student or third year or final year student? Is there a disturbance? Deva, please let me know, is there any disturbance? I will definitely help you, don't worry, dear. Just let me know the topics. Is there any sound disturbance, voice clear, background noise, anything? Just on the fan. Are you getting any disturbance because of this fan? Please let me know. If that is the case, I'll try to off it. Deva, please let me know the audio clarity, dear. Shall I off it? Yes, I think a bit. Okay, no problem. No problem. I can manage. Which ionosphere layer is responsible for return of radiation at frequency of 30 megahertz? No problem, Deva. It is not that important. I can manage the heat. Ionospheric propagation or skywave propagation is between 2 megahertz and 30 megahertz. So he is asking which of the ionospheric layer is responsible for the return of radiation of frequency at 30 megahertz. Curvature of the earth. Above the earth's surface from 50 kilometers, ionosphere will start. 50 to 90 kilometers, it is D region, which has a critical frequency of 100 kilohertz. Frequencies not more than 100 kilohertz are reflected by the ionosphere. D layer. E layer. E region is critical frequency between 3 megahertz and 5 megahertz. F layer or F1 layer 5 to 12 megahertz. Above 12 megahertz is F2 layer. I want to reflect 30 megahertz, means highest frequency possible. Highest frequency that is possible by the ionosphere I want to reflect. So naturally that will be done by the topmost layer. As you move up, the critical frequencies will increase. Digital communication concepts, data communication codes, serial and parallel interface, network protocols, types of satellites, advantages of optical fiber. Most of them we had covered, Deva. In our previous series, if you go through previous series, most of them I had covered. But I will take up all this. This is into advanced communication. The topics that you are asking are into advanced communications. We took one series on advanced communication, even on app. On app also I took a series on advanced communication where we had exclusively covered all these things. But if you want, we'll also try to plan one series on this. Okay, don't worry. Okay, no problem, Deva. Fine. So, which ionospheric layer is responsible for the return of radiation at frequencies of 30 megahertz? 30 megahertz means topmost. For higher frequencies, F2 layer is responsible. F1 and F2 put together at night, F1 and F2 are combined to form as F layer. F layer is responsible. Option C is the answer. Next, match list 1 with list 2. List 2 is type of radio waves. Select the correct answer using the code given below the list. Now, tell me the answer, Deva. Microstrip line, earth crust. These are the medium. Troposphere, ionosphere. Types of waves: surface wave, guided wave, sky wave, space wave. Try to answer. Dear. Try to answer. Yes, dear. What is the answer? What is the answer? microstrip line is a feeder. Microstrip line is a feeder that is used in microstrip patch antennas or microstrip array antennas. It's a guided structure. If using a microstrip line, it will send a guided wave. It acts as a waveguide. Along the earth crust, you send surface waves or ground waves. Ground waves are also called as surface waves. Through troposphere, we use line of sight communication or space waves. Through ionosphere, we send sky waves. Microstrip line refers to guided waves, that is 2. Earth crust, surface waves. Troposphere, space waves. Ionosphere, sky waves. 2, 1, 4, 3. What's the answer here? Option D is the answer. 2, 1, 4, 3. Option D is the answer. Is it clear? A duplexer is used for which one of the following? I repeat it. A duplexer is used for which one of the following? To couple two antennas to a transmitter. This is a transmitter. Do we use duplexer to couple two antennas to a transmitter? Is it the case? To isolate antenna from local oscillator, because you'll have a local oscillator here in the transmitter. To isolate antenna and local oscillator, do we use duplexer? To prevent interference between two antennas connected to a receiver. When we connect two antennas to a receiver, in order to prevent interference between these both, do we use a duplexer? Or to use same antenna for reception or transmission without interference? What's the answer here? Think and answer. Think and answer here. What is the answer? Think carefully and answer. I'm just waiting. Think and answer. We can use a circulator, application of a circulator. We can use a circulator as duplexer. See how it works. Port 1, port 2 and port 3 of a circulator. At port 2, you had placed an antenna, and at port 1, you had placed a source, and at port 3, you had placed a receiver. Source will send a signal which will feed the antenna. Remember, in a circulator, only clockwise movement is allowed. Of course, that we had discussed in microwave. Please go through the microwave concepts video, in which I very clearly discussed about the microwave components, where I explained how this is possible. So, in a microwave component circulator, the movement will be only in the clockwise direction. So, once I feed this antenna using the source, this antenna will start to radiate. VI waves are converted to EM waves. It is acting as a transmitting antenna. Far away, there is one receiver. Here, it is received by the receiver. One more transmitter is there here, which is transmitting the signal to this antenna. Now, this acts like a receiver. This is received by the antenna. Then it can only transmit to the clockwise direction. In clockwise direction, there is receiver. So that is received here. So this source signal, whatever it is giving, it is transmitting. It is acting as transmitting antenna. Whatever signal is received by this source here is received by this receiver. So the same antenna, we are using it for transmitting and reception without any interference. This is the main work of a duplexer. If you know the working principle of a duplexer, this was a very simple question. On the other hand, if you don't know the working principle, naturally it looks difficult for you people. Am I right? Is that clear now? So what's the answer? Question number 20. Duplexer is used to use the same antenna for reception or transmission without interference. 21. For obtaining a beam of electromagnetic wave with circular polarization, what is the ideal antenna? I told you. Circular polarization. Which antenna is used? For circular polarization, we use which antenna here? For a circular polarization, pair word is we use helical antenna. We use helical antenna for circular polarization. Question number 21. Option B is the answer. Duct propagation of microwave occurs. Duct propagation is mainly due to formation of inversion layers. In an inversion layer, generally in troposphere, as we move up, temperature falls down and it falls at the rate of 6.5 degrees Celsius per kilometer. But when there is region with highly water vapor, instead of decrease of temperature, with the increase of height, temperature will increase with height. In these conditions, we say that inversion layers are formed. And due to the formation of inversion layer, a duct-like structure is formed over the oceans, or over the water bodies, or in the coastal regions, where the humidity is very high and the formation of inversion layer is very frequent. So what is asking? Duct propagation. Now the propagation through this duct is called duct propagation. Duct propagation of microwaves. Why is saying microwaves? Because duct propagation frequencies allowed at 300 megahertz to 30 gigahertz. Most of the microwaves occur due to which one of the following? Variation of refractive index N with wavelength, with length, with height, or none. This is Earth surface and this is the duct. Inversion layers are formed. That means what is happening to refractive index? N1, N2, N3, N4. It is changing in this way. What is changing? Refractive index is changing with what? Height. Variation of refractive index with height. Simple question, but logical one. You should be very careful, okay? 22nd question, option C is the answer. 22nd question, option C is the answer. Is it clear? Next one. Tropospheric scatter communication is used for which frequency band? If you know the frequency bands, it will be very easy for you. First, let me explain. What is tropospheric scatter frequency? 100 megahertz to 10 gigahertz. This is the frequency range. Now let me know the frequency ranges. High frequency waves, 3 megahertz to 30 megahertz are called high frequency waves, which are also called as short waves. Below that, we have medium frequency waves, which are from 300 kilohertz to 3 megahertz. And these waves are called medium waves. Below that, 30 kilohertz to 300 kilohertz, low frequency waves. These waves are called long waves. But the wavelength is long, frequency decreasing, no? Below that, very low frequency waves, 3 kilohertz to 30 kilohertz wavelength. These waves are called very long waves. Above high frequency, it is very high frequency, 30 megahertz to 300 megahertz. Now you see the range. This fellow is starting at 100 to 300. So in VHF, how much bandwidth is there? For tropospheric scatter propagation, 200 megahertz bandwidth is there. That means from 100 megahertz to 300 megahertz. In VHF, that much bandwidth is allowed. Above VHF, it is UHF. 300 megahertz to 3 gigahertz or 3000 megahertz. Now if you see here 300 megahertz is there. Up to 3 gigahertz, everything is allowed. Means how much bandwidth is allowed in UHF? 2700 megahertz bandwidth is allowed, which is in UHF. Above which it is super high frequency, 3 gigahertz to 30 gigahertz. This fellow is allowed up to 10 gigahertz. So 7 gigahertz bandwidth is allowed here in SHF. Mostly tropospheric scatter is in SHF. But is there any option of SHF here? No. So out of the available bands, which band is taking more one? Actually it is SHF, but SHF is not available. So once you remove SHF, in which band you have more bandwidth? UHF. Therefore you can go for UHF. Because you want to select one. Otherwise, in general, tropospheric scatter will allow VHF, UHF and SHF. Specifically in VHF it will allow 200 megahertz. In UHF it will allow 2700 megahertz. In SHF it will allow 7 gigahertz. So you should be very careful here. You should think and write the answer. Any doubt here? Hopefully I cleared the doubt. Is that clear? Everyone, is that clear? Okay. Next question. Which of the following antennas uses a number of varying length parallel elements? Helical antenna, coaxial cable, inner cable, reflector sheet, inner cable turned into helix. Helical antenna, number of varying length parallel elements, not possible. Pyramidal horn, waveguide, extended structure like this. No parallel elements. Corner reflector, we will have something like this with the horn antenna. This giving spherical wavefront, the corner reflector converting the spherical wavefront into parallel wavefront. No parallel elements. Yagi-Uda antenna, yes. The driven element is generally the folded dipole antenna. At the driven element, the reflector, which is 5% greater than the driven element. Then series of directors decreasing height and placed parallelly. There's an antenna, this is a horizontal rod and this is a vertical rod to support. This is a Yagi-Uda antenna. Yes, Yagi-Uda antenna is something which has number of varying length parallel elements. Very simple question, but sometimes it happens. This is an engineering services exam, not a simple exam here. Sometimes you'll ask simple questions also. This is one of that model where the simple question is asked. Question number 24, option D is the answer. Is that clear? Good. Next. 25th question. In the ionospheric layer, ionosphere layer, the lowest frequency signal that penetrates the layer upon vertical incidence. Frequency related to vertical incidence is called as critical frequency, which is given as 9 root n max. We have derived this. 9 root n max is not there. Take the 9 inside. Under root of 81 n max. Under root of 81 n max is present. Option C is the answer. Question number 25. Option C is the answer. A radio cap company with its antenna at a height of 15 meter communicates with a cap having its antenna of 1.5 meter. The maximum communication distance without obstacle range. It is using line of sight formula 3.57 into under root HT plus under root HR kilometers. Please do it now. Calculate the range and tell me the answer. I am also doing. You people also do it here. You people also do it and tell me the answer. Yes, calculate. (3.57) into under root HT under root 15, 3.87. Range is 3.57 into under root HT under root 15 plus under root 1.5 kilometers. This is 3.57. Under root 15 is 3.8729 plus under root 1.5. 1.224. When you add up 3.8729 plus 1.224, this is 3.57 into 5.0969. 5.0969 into 3.57, which is 18.1959 kilometer. Closest answer is 20, or you can take the range formula, 4 times of under root HT plus under root HR kilometers. Then this will become 4 times of 5.0969. 5.0969 4 times is exactly 20.3. Closest answer. Anyways, both the cases, closest answer is B. Option B is the answer. Question number 26. Option B is the answer here. Next, microwave links are used for TV transmission because they have small signal to noise ratio. Small signal to noise ratio. See the question carefully. Small signal to noise ratio means more noise. Microwave links have less noise. They have more signal to noise ratio. This is not true. They produce less phase distortion. They are relatively cheaper. No, they are costly. That's the drawback. They are free from impulse noise. No, they are not free from impulse noise here. Even at microwave frequencies, impulse noise will have effect. So, by elimination method, only one is there. They produce less phase distortion. They produce, one of the advantage of microwave link is they produce less phase distortion, and in TV, by the change of phase, signal information will vary. Therefore, for TV links we use microwave links for TV transmission because they produce less phase distortion. Option B is the answer. If the receiving antenna is polarized at 90 degrees with respect to transmitting antenna, it will receive 90-degree polarization. Means if you give horizontal polarized wave, the output will be vertically polarized wave. If you give vertically polarized wave, the output will be horizontally polarized wave. Therefore, when you have 90-degree polarization, if you give horizontal, it will give you vertical. If you give vertical, it will give you horizontal. If you are transmitting from a horizontal antenna and the receiving antenna is a vertical antenna, it will not receive anything. No signal is received. Option A is the answer. 28 question, option A is the answer. Is there any doubt? Clear? Twenty-ninth question. The efficiency of an antenna having a resistance of 30 ohm, loss resistance is given as 30 ohm, radiation resistance is given as 60 ohm, percentage efficiency is asking. Percentage efficiency is RR by RR plus RL into 100. 60 by 60 plus 30 into 100. 60 by 90 into 100. 6 by 9 into 100. 2 by 3 into 100. 0.667 into 100. 66.7 percentage. Closest one. Option C is the answer. Question number 29. Option C is the answer. We'll go for more practice questions in Antennas Maha Marathon 18, which will start at 6 a.m. today because it has crossed 12 already. 6 a.m. today. We'll have Antennas Maha Marathon 18. Okay? Antennas Maha Marathon 18. We'll discuss in Antennas Maha Marathon 18. We will do so many practice questions dear, nothing to worry. Unacademy provides two paid platforms. One is Plus subscription, other is Iconic subscription. In Plus subscription, you got to have the face time of legendary faculties in the form of live classes, weekly tests, structured courses, unlimited access, rank improvement batches and crash courses. In Iconic, you'll have all these features. Along with that, you'll have a dedicated personal coach for one-on-one guidance, dedicated doubt clearing educators to clear doubts within 1 hour, preparatory study material which is nothing but specialized notes and practice sets, personalized test analysis, study booster sessions and customized study planner. All this in Iconic subscription. If you're going for a Plus subscription or an Iconic subscription, I recommend you to go for a no-cost EMI. That means total cost will be divided by number of months without any extra cost, which is student-friendly. And you can go for our team code. Remember, team code. We don't promote personal code, but we promote team code here. Our team code is KNR10, by which you will get 10% off. Not only that you get 10% off, but the advantage of using our team code is the complete team, KN Rao sir and team, will be with you. This is a unique advantage that you have, that you can use our team code. The complete team will be with you. With Iconic subscription, we will get 1:1 live mentoring program, which increases your chance of getting a top rank. Offered alert here, with every 24-month subscription, we are giving away 4-month subscription free, which is valid up to the 25th of February. And with every 12-month subscription, we are giving away 3-month subscription, valid up to 25th of February. And this is GATE and ESC Mega Combat. Combat is nothing but a live quiz competition where we'll ask 20 questions. 60 minutes will be given. Conducted on Sunday, 11 a.m. Separate paper will be given for mechanical, civil, electrical, EC and CSIT. 20% guaranteed scholarship you will get, and 500 lucky participants will also win all these exciting prizes. We are ready to give away 4 crore as scholarship, and the toppers will get 100% scholarship, and it is free to enroll. Just you can use our team code KNR10. If you are having any doubts in your preparation journey, subscription and latest offers, you can talk to our counselor. This is the number where you can directly talk to our counselor. The super combo offer. With every 2-year subscription, we are giving away 1-year subscription free for campus placement and IT jobs. With every 1-year subscription, we are giving away 6 months subscription free for campus placement and IT jobs. This is a rank predictor which is out now. Just log in and sign up to Unacademy. Go to GATE landing page. Click on rank predictor banner. The link is given here. Select your stream. Select session appeared. Paste your URL. You will get your rank. These are special class features here where you have interactive live classes for the learners, poll for the learners, raise hand option. You never miss a class when the notification is on. You can download the lecture notes. Once the class is done, you can access anytime and anywhere. We are introducing community here, through which you never miss any update from your favorite educator. You get the session notes and practice material. You can share your feedback directly via polls. These are the new batches dear. As you know, every week we start 6 to 7 new batches. These are the batches which are started on 16th of February. Resilience GATE 2023 for electrical explained bilingual. Resilience GATE 2023 for ECE explained bilingual. Ascent GATE 2024 for ECE explained bilingual. Ascent GATE 2024 for electrical explained bilingual. Evolve Gate 2023 for electrical explained bilingual. These are the new batches across all the branches. You can join any one of them. You can use our team code KNR10 to get extra 10% off and the team support. All the best, dear. All the best, everyone. And thank you for joining the session. Thank you all.